a few things today about EKG. I want to make sure we're all clear on what we're using for EKG in terms of what the basic beat looks like, and then an approach to analyzing EKG. I will tell you that I don't have the only approach to EKG. You can make whatever arguments you want about whether or not my approach is the best or not when it comes to EKG, but you have to have an approach. So if you don't have an approach, you might as well use mine. But if you want to find a better one, feel free. But when you're confused on EKG, the very first thing that I'll start talking to you about is how do you approach an EKG. And how that happens, how you approach those, will make a very, very huge difference in the end on whether or not you come up to the right conclusions and the right answers when you talk about it. So when we talk about the basic beat, remember that that basic beat included what? What did I say a cardiac cycle was? Good. And a T wave. Good. So it was a P wave, a QRS complex,
and a T.
And a T wave. And anything else that follows the T wave, and anything else that comes before the P wave but is related to that one beating of the heart. Okay? So a cardiac cycle under normal circumstances starts with a P wave and ends with the next P wave. And that includes both the systole and the diastole of the heart. Does that make sense? So from P wave to P wave, from beginning of P wave to beginning of P wave, and from the standpoint of depolarization, it means from the moment the SA node fires to just before the next moment the SA node fires. Make sense? Okay, so that's our basic beat. That basic beat includes, that waveform includes up to, or a combination of 3 different things. We either have a wave, a segment, or an interval. And a wave is any motion off the baseline. Okay, so we're going to use some line here that we're going to refer to as the baseline. That baseline is most commonly going to be found between the T and the P wave, which I'll come back to in just a minute, and we'll name it. But a wave is any deflection off the baseline. A segment is any portion of the baseline between waves. Okay? Any portion of the baseline between waves. And then an interval is any combination of at least one wave and at least one segment. It could be more waves, and it could be more segments, or a combination of several waves and several segments, but it has to include at least one wave and at least one segment. Does that make sense? So when we name these things, we have the first deflection off the baseline in our cardiac cycle is a wave that we named what?
P wave.
Good. We named this the P wave. Right after the P wave starts what?
PR interval.
A segment. Yes. This segment that goes from the end of the P wave to the beginning of the QRS complex. And we refer to that as the
PR segment.
Just the P. That's yours.
Thanks.
You bet. We've referred to that as the PR segment. I will tell you that there are some references, some books, that will refer to that as the PR or the PQ segment as well. Because some references talk about the fact that the Q wave is first, but most references, and how I'll always talk about it in here, is related to the PR, because a lot of times the QRS complex is abbreviated just R. Okay? But when we say the PR segment, we're not saying from the end of the P wave to the R wave. We're saying from the end of the P wave to the beginning of the QRS complex, and we're just abbreviating it with an R. Does that make sense? Okay. That's followed up by a series of individual waves, and those individual waves can be what?
Up or down.
They can be up or down. And what have we named them before?
QRS.
Q, R, and S. Those are individual waves. I'll define those waves later, but those are individual waves. We have the Q, R, and S, and we refer to that as the QRS complex. Does that make sense? Okay. After the QRS complex, what's next? Yeah, good. A segment. A segment that ends at the end of the QRS complex. Sorry, it begins at the end of the QRS complex, and it ends at the beginning of the T wave. Good? So this section right here is what we'll refer to as the ST segment. Now, it doesn't matter if there's actually an S wave. It doesn't matter if there's an S wave. You might have a QRS complex that does not have an S wave, and it just ends in an R wave. We still don't call it the RT segment. It's still called the ST segment. Does that make sense? We'll always keep that name the same. In addition to that ST segment, the point at which the ST segment begins, right at the end of the QRS complex, is something that we refer to as the J point. And that J point is going to be of critical importance to you. The J point. It is the point at which the ST segment begins. After the ST segment, then what do we have?
T wave.
And then we have our T wave. Good? At the conclusion of the T wave, what do we have?
U. Sometimes.
TP segment.
Good. So we can have a variety of things. It's possible we have a U wave. In some cases, there is a U wave. Under normal physiologic considerations, we typically don't see a U wave. We'll come back to when we do. And so the end of the T wave to the beginning of the next P wave is what we refer to as the TP segment. Make sense?
Mm-hmm.
Questions on that? Yeah,
You said you go over the U wave later?
we will. We'll discuss U wave.
Never mind.
Okay. So when we talk about the baseline can go by two different names. You either have baseline, which is perfectly fine to refer to it as baseline. You also can refer to it as the isoelectric line. Baseline or the isoelectric line. I will tell you right now that I will often use those words interchangeably, and I don't necessarily have a rhyme or reason for why I'm using it. Or in my head, I probably do. If I'm speaking if my mind is working in more physiologic terms, I'll probably use medical terminology and call it the isoelectric line. And if I'm speaking more in clinical terms, I'll probably refer to it as the baseline. It doesn't matter. They're completely interchangeable. Good? Baseline and isoelectric line. Under most circumstances, the place that you want to look for to find where that isoelectric line actually is from the TP segment. So a couple of weeks ago, I gave you a ruler. Yes, I gave you a laminated ruler. And that laminated ruler was translucent. You could see through it, and it had a red line in the middle of it, right? The way that we use that to find our baseline would be to set that ruler on our EKG, so we can still see the EKG in the background, and put that red line on our TP segment, and follow it from that TP segment to the next TP segment, so that both of these two TP segments were on that line. And as that line cuts through the entire cardiac cycle, that's our isoelectric line. Why it's important to do that is because some of our waves and some of our segments won't be on the isoelectric line like they're supposed to be, which in fact is something we need to note, because that's something that we're looking for, or something that defines what the problem is that that patient is having. If a segment and or a wave is not on the isoelectric line when it's supposed to, that tells us something. But sometimes it's difficult to see that in a rhythm that's all crappy. And so we use a tool to be able to make sure that we know where that isoelectric line is, and then we can evaluate if things are above or below it. Does that make sense? So again, typically what you'll do is you'll put a ruler against the TP segments between one segment and the next, and then be able to look at what's happening to the rest of the cardiac cycle inside that, underneath that ruler. The PR segment, the ST segment, and the TP segment in a completely normal physiologic individual should all be on the baseline, all the way through. And that ruler should be able to hold several different cardiac cycles with the PR segment, ST segment, TP segment all being on the line in each of them all the way through. Does that make sense?
Yes.
Okay, excellent. So, P wave, PR segment, QRS complex, ST segment, T wave, and the TP segment are our segments. Then when we start mixing up intervals, an interval is what? At least one wave and at least one segment. So we have intervals here. One interval starts at the beginning of the P wave, so it includes the P wave, and ends at the end of the PR segment, so it includes the P wave and the PR segment, and we call that the PR interval. And again, some references that you read, don't be confused, we'll call it the PQ interval. That's rare, not very many places do that, but there are some references that do call it the PQ interval. They mean the same thing most places, and I will always use the PR interval for our naming here, okay? So that's one interval. We also have what's called the QT interval, and I realize that in medicine sometimes there's some things that aren't uniform, because you could just as easily have called that the RT interval to match it with everything else, but it's not. So from the beginning of the QRS complex, including all waves within the QRS complex, including the ST segment and including the T wave, gives us the QT interval. Okay? So in this case, the PR interval is one wave and one segment. In the case of the QT interval, it's at least two waves and one segment, and could be as much as 4 or more waves and a segment, depending on what's happening in the QRS complex. So that's our QT interval. Make sense? We also have an interval that goes from the beginning of the P wave to the beginning of the next P wave. And that is referred to as our P to P interval. Okay? And we can have a wave that an interval that starts at the beginning of the QRS complex, going to the beginning of the next QRS complex, and we refer to that as the R to R interval. That make sense? P to P intervals and R to R intervals end up including everything within a cardiac cycle. Does that make sense? No matter where you start, right? P to P includes everything in this cardiac cycle, and the R to R includes everything, includes all the waves and segments between these two cardiac cycles, even though it doesn't include all of a single cardiac cycle.
So an interval is distance measured as time between at least two cardiac events?
Nope, between at least a wave, to include a waveform and a segment. An interval is any period of time in the cardiac cycle that includes at least one wave and at least one segment.
And R to R is truly from the R to R, not.
No, the R to R is called the R to R because it's going from one QRS complex to the next.
Beginning of the Q.
So you can do it any number of ways. You can do it from beginning of Q to beginning of Q. You can do it from peak to R to peak to R. You can do it from trough of S to trough of S. It just has to be the same spot in those two QRS complexes. The reason why it's referred to as the R to R interval, once again, is because we abbreviate QRS with R, and the peaks of the R typically are easier to find sometimes than the beginning of the QRS complex. So we jump it from there. Same with the P to P interval. The P to P interval is literally the beginning of the P to the beginning of the P. We often will measure it from the peak of the P to the peak of the P because it's easier for us to find it. It just has to be the same spot in the wave to the same spot in the subsequent wave. That make sense? Questions? Okay, you can make some determinations on your own on some of this. For example, if you have a patient who is at rest and they're going to continue to be at rest for a window of time, let's say for the next 10 minutes, where they're not doing anything to engage either the sympathetic or the parasympathetic beyond what is currently engaged, yes, then you can make some assumptions about them. And let's assume for a moment that there are no, I know that some of you love my tangents. Did you ever see this before? Did you ever see that before? Where people will say, when you assume, it makes an ass out of you and me, and you shouldn't assume. Did you ever see that before?
But
It's the first.
I've never seen that.
I haven't either.
See? It's a first.
Not the only one.
I guess I should
Good.
assume that you've seen that before.
How many of you are driving home today? Really? Are you sure about that? Is your car out there?
No, mine's not.
Those of you that drove here, your car's out there?
Yes.
Yes.
Just checking for.
How do you know it's out there? How do you know it's not been
We
stolen?
assume it's out there.
I have GPS on the phone.
Are you gonna go through a light on your way home?
yeah.
How do you know you're gonna leave the parking lot, let alone go through a light?
Not scary.
Gosh.
When you go through the green light, are you gonna get through without someone hitting you?
I hope.
Hopefully.
This is BS. We don't need to teach people to not assume. We need to teach people to assume better, right? You can make assumptions. Assumptions are perfectly fine to make. Just make sure that they're educated assumptions, right? You assume all day long in every which way. You assumed I was going to be here to teach this class today. But there was no guarantee I was going to walk through that door. I assumed all you were going to be here. But there's no guarantee that you were going to be here, right? Okay, so keep that in mind. We assume in a person that is completely normal in their physiology and they're at rest, we can make some assumptions on what we're going to see in their cardiac cycles. For example, we will assume their SA node is working, and if their SA node is working, the pathway that their electrical current is going to take from the SA node through the ventricles will be the same every single time. If it's going to be the same every single time, if the pathway is the same, then what will the P waves be compared to each other?
Same.
Same.
They gotta be.
Regular.
How long will the AV node delay the signal in one cardiac cycle compared to the next one?
Same.
The same. Therefore, how long will the PR segment be in each of those?
Same.
Therefore, how long will the PR interval be in both of those?
Same.
And if the QRS complex has a certain look to it, whatever that look happens to be, what will the next QRS complex have in its look?
Same.
I assume the same.
Isn't that amazing? Isn't that amazing? Yes? All right. And what will the T wave be compared to the next T wave?
The same.
Okay, let's blow some minds. Ready? Ready for your mind to be blown?
It's not the same.
All right, here you go. Watch. No, I'm not going to blow your mind that way. But let's say that this T wave looks different. I don't care what it looks like. Let's say it looks different. But the P waves in all three cycles look the same. The PR intervals in all three of those cycles are the same. The QRS complexes in all three of those cycles look the same. The P to P intervals are all the same. The R to R intervals are all the same. What can you say about that T wave?
Speed bump.
Can you watch
Anomaly?
it?
Just different.
Outlier?
Artifact.
Something's weird.
Say it again.
Artifact.
Something else not related to their physiology is affecting the EKG at that moment in time.
Speed bump.
Talking, breathing, who knows?
Could be. Because there is nothing that would contribute to that T wave looking different. Because think about it, what does the T wave represent?
Ventricular
repolarization.
Yes, and what are two big category things that happen during repolarization? Oh, please tell me. It's a physiologic thing. You learned about it in A&P.
Absolute refractory period?
Yes. If this T wave is going to look different, if that T wave looks different because it's repolarizing differently, then it will also have a different absolute and relative refractory period in that moment, yes? And if the absolute and relative refractory periods are different at that time, then the timing of the next beat will also be different. Because you can't have a refractory period that is different and not affect everything else that's going on around you. So if everything looks the same, and you have one little anomaly, you question what that anomaly is, and in some cases, it has nothing to do with the heart. Does that make sense? Okay. Mind blown yet?
No.
Okay, good.
Halfway.
Halfway blown. Well, halfway is better than whatever it is. There you go. All right.
Halfway brain.
Come on, let's have some nuts.
That'll help, man, thanks.
So, the
Yes.
definition of an artifact is something that you see on the EKG that was not created from the
Yes.
heart.
Artifact literally is anything that adds to an EKG that has nothing to do with the heart. It could be a person's cold and they're shivering,
Sometimes.
and their shivering is causing an artifact. It could be you're in an ambulance with a 60-cycle engine pumping away and it's putting vibration into the person. It could be that they're breathing. It could be that they're sneezing. It could be that somebody's beating them at that moment in time. Whatever the case is. You know, I put my kids on EKG and then I start smacking them around. It's kind of fun to watch what happens in EKG, right? So it's great. And now that's recorded.
Now we all get to
It's on the
hear it.
internet too.
You know, it is what it is.
How exciting.
They come back for more, so I don't know what to say. The P wave. The P wave. When I'm talking right now, we are going to make an assumption. We are going to assume that they are completely normal in this moment in time. And we're going to stay away from the what ifs, because the what ifs are why we're called. Right? Okay, so assuming that they're normal, the P wave will be the first wave in an EKG cycle. It's our first wave that we see. Okay? It is a representation of the atrial depolarization, and it starts after the SA node fires. The SA node is what initiates the P wave beginning. It does mean that even though we don't see it, the SA node fires a fraction of a millisecond or so before the P wave. Okay? The P wave is the atrial depolarization. I won't make you know this timing right now. There are some of the times that you will have to know. I'll make that clear in one moment. But it can vary between about 0.08 to 0.11 seconds, and the time is important. It's just not important today. It'll become important later, but not today.
I have a question.
You betcha.
So is the time, if the time is going to be important, is the y-axis going to become important?
Yes. Both
Okay.
axes are important.
Are we going to learn
No.
the degrees in which that number is going to be augmented based on where the picture is being taken?
Yes. Or at least you will understand, at least initially, proportion of size in one lead compared to another, based on where those cameras are.
Is that going to be a whole other set of numbers memorized versus?
Yes.
Okay.
Although less for the P wave and more for the other intervals and waveforms that I'm going to talk about next.
Okay.
Okay. The word axis, when we talk about axis, we are talking about the general and average direction that electrical activity is traveling. Okay? How many of you got to LCC today by driving south on I-5 before you got off on the exit? Fantastic. So there's a few of you. How many of you drove over 30th Avenue to get here? Okay, so about an equal number of you. How many came from I-5 south and came up north? Okay, so there's 3 of you. You were driving north on I-5 before you got off, because there's 4 of you that were driving from south to north. Okay? So there were twice as many of you that were coming from the north to here than from the south. Does that make sense? So if I had to break it down and say the direction my students come from to get to this class, and I could only say one direction, I would say they're coming from the north. Are they only coming from the north? No, there are some coming from the south. And if I really want to be correct, I've got some coming from the north and some coming from the northwest. But generally speaking, I have a northward flow to get here. Does that make sense? Okay, so in the heart, you have waves that are going all over the place. You have some waves that are coming from these cells down to these cells, some that are going from these cells over to these cells. because of gap junctions, yes. Some that are coming from these cells, slightly up to these cells. But the overwhelming majority of the cells in the P wave are coming from a top right to bottom left direction. So they're coming this general direction. They're moving downward and to the left. Does that make sense? That overall general direction is what we call the axis. And so the P wave axis is traveling from 0 degrees to 75 degrees. We'll talk about the degrees later, but that means it's either going this way to this way. That's the general flow in most people for that P wave. Does that make sense? Don't worry about the degrees. Yes, you do need to know the degrees of axis, but we'll get to that when we talk about axis. Right now, understand what axis is, and that's the general flow for the P wave. And that should make sense, right? With the SA node being in the top right of the atria, and all of the other cells, for all intents and purposes, being below it and towards the left, that's the general flow of electrical activity. Make sense? Excellent. Okay, and so we have that P wave. Yay for the P wave. Good. We mention it more in academics rather than actually meaning something, but do be aware that when we have the P wave firing, we do have the P wave that has its own refractory period and its repolarization period. And that repolarization period is something that we refer to as the TP wave, and you never see it.
Why is that negative deflection?
That is such an excellent question. You think about that for a minute, because when we get to the T wave, I'm going to ask you to give more information about that. So that's a critical question that she just brought up. You just don't know it yet, but you will. So we have the P wave followed by what's referred to as a TP wave that never shows up on an EKG. Very rarely will it ever show up. First of all, when it is there, it's almost always covered by a QRS complex, so it's mixed into the average of the QRS complex, so we don't actually see it. If we don't have a QRS complex, but we have a P wave, we still usually don't see it, because in that in that usual sequence, the reason why we have a P wave and no QRS is because the person's about to die anyway, and their P wave is so slight that we don't see the TP wave that way either. But when we would actually really be able to see a good TP wave is when we have a completely healthy atria and we somehow cut the ventricles out. And that's not very common in normal humans, right? And it's not ethical to do that to a human, so we don't typically see it. But it is there, and sometimes it does disrupt some things a little bit. Sometimes it can make a little change in the QRS complex that goes, oh, what's that? Huh, something's a little weird there. Yes, ma'am.
I got a question. So is the QRS negative deflection that happens right there, is that the initial part of the TP?
No.
Or is that, okay.
It's its own complex, and I'll cover it in like
Okay.
6 minutes, maybe 4. The PR segment, again, is that space that happens after the P wave and before the QRS complex. If it is greater than 0.8 millimeters off the baseline, there's something pathologic. When I talk about millimeters, that means north and south. When I talk about milliseconds, it means east and west. Time is on the x-axis. Amplitude, that we're going to measure in the form of millimeters for now, is on the y-axis. So if it is off the baseline, north or south, by 0.8 millimeters, so one small little box in the EKG, which I'll get back to in a little bit, then we would say there's something not quite right with it, something's going on. We'll discuss what those pathologies are, but something's not right about it.
One box is 1 millimeter.
One little box on an EKG is 1 millimeter, and I'll show that in a little bit.
How many millivolts is that?
Well, it's not a direct correlation to that, because remember, we're talking about impedance and we're talking about
that's right,
a proportion that comes into play. So although it's linear, it's not exact. Okay, and then we have the PR interval. And we remember the PR interval was that thing that starts at the beginning of the P wave and goes to the end of the PR segment, or the beginning of the QRS complex. We call that the PR interval. And the PR interval involves a whole lot of stuff, right? It is the initial impulse of the SA node. Yes, the SA node is just a hair before that, but we do include it in the talk of the PR interval. It includes all the atrial depolarization, all the atrial the atrial repolarization, but not necessarily the look of that will happen in there. It'll initiate in there. We'll see the AV node stimulation, the bundled His stimulation, the bundled branches, and the Purkinje system. All the autorhythmic cells will have fired, and all of the atrial cells will have fired. Repolarization at TP can kind of move itself a little bit from place to place, but everything else is already fired, and the only thing left to fire are the ventricular contractile cells. That PR interval holds a whole lot of importance. A whole lot of importance. So, beginning of the P wave to the beginning of the QRS complex. Okay, your first thing you have to know, the duration. Not the first thing you have to know in this class, but the first time. The PR interval needs to be between 0.12 and 0.20 seconds. Between 0.12 and 0.20 seconds. If it is shorter than 0.12, there is a problem. If there is greater than 0.20 seconds, there is a problem. So it needs to be between and including 0.12 to 0.20 seconds.
Does its shortness or greatness indicate the magnitude of the problem?
Not necessarily. No, because then you take into consideration some of the pathology and that kind of stuff. And that has to do with just the location of where what focus is firing, and that does not necessarily dictate a magnitude of problem. So 0.12 to 0.20 seconds is what we're looking at. And then if it's less than 0.12, there's a problem, and if it's greater than 0.20, there's a problem. If it's less than 0.12, the pacemaker is not the SA node. And if it is greater than 0.20, there's a block someplace in the AV node.
If it's less than 0.12, the SA node is not the pacemaker.
Correct. So when you look at the heart, right?
Okay.
There's the AV node. Right? If the SA node, the time it takes for the signal to get from the SA node through that AV node and on down, that pathway, takes X amount of time. If the SA node is out of the mix altogether because of drugs or because of damage or hypoxia or something else, and a different pacemaker takes over, then it'll be a shorter time. And therefore, the PR interval will be shorter.
That signal will travel both ways, right?
And that signal will travel both directions. That's correct. If there's something happening in here that creates a block that doesn't allow the signal to travel as quickly, so the signal is working fine from the SA node, it's going fine from the SA node on down, it gets to the AV node in its normal time, but the AV node holds on to it for a little longer than it normally should because the signal is not getting through, or there's some sort of a block that the signal has to get around before it can continue on down, then it will delay when the Purkinje fibers can give the signal to the ventricles. The QRS complex is related to the ventricles. So therefore, there will be an elongation of the PR segment, and the PR interval will take longer than 0.20 seconds.
What can cause a heart block?
Any number of things. It could be drug-induced, it could be vagal stimulation-induced, it could be trauma, damage to the area, trauma to the site, it could be hypoxia to that site, it could be an anatomical problem that a person has.
How it is?
Yep, there's any number of different things that could lead to that, of which we're going to talk about many of them. Good? Okay. So that's our PR interval. The QRS complex represents that ventricular depolarization. It has it potentially has a Q wave, an R wave, and an S wave. So it potentially has all of those things. And so let's talk about all of them for a minute. So the Q wave may or may not be present. It may or may not be present. The R wave is always a positive deflection. The S wave is always a negative deflection. I'll get to that in a second. And the R wave is always called the R no matter what. The positive deflection is always called an R, regardless of whether or not there is a Q wave or not in that place.
The Q wave is always negative also?
The Q wave is always negative, and I will give more information on the Q wave in just a moment. The Q wave is always negative. Chandler, was that a question? Or was that not a question? So the Q wave is always, and listen to my definition carefully, it is always, except for in one circumstance, the first negative deflection after the P wave if the first deflection after the P wave is negative. Let me say that again. The Q wave is always the first negative deflection after a P wave if the first deflection, positive or negative, after the P wave is actually negative. Does that make sense? Then we call it a Q wave in all but one circumstance, which I'll explain in just a minute. All positive waves, every one of them within a QS complex, is called an R wave. All positive waves in a QS complex are R waves. And you might have more than one. All negative deflections in the QS complex, except the Q wave, are called S waves. And you might have more than one S wave. So every subsequent negative deflection in the QS complex is an S wave, except for when you have a Q wave. You could look at it this way. Every single negative deflection after the first R wave is an S wave. Does that make sense? The one caveat is if you have a QRS complex that looks like this. Only one negative wave. If you have only one negative wave, in which case we call that a QS wave. Good? So a Q wave is what?
First negative.
The first negative deflection after the P wave,
Negative.
if the first wave is negative. So what if I had this? What if I had,
No Q wave.
so what do I have?
RS.
I have an RS. What do I have here?
QR.
I have a, what do I have?
QR.
I have a QR wave. And here, a
QRS.
QRS. Does that make sense? What if I had this?
Oh my god.
R.
Good, QRRS. That's correct. And when I have two R waves, the second one is given a prime node. So I have my R wave and my R prime. And if I have two S waves, I would have an S and an S prime. And if I had another R wave, before I came down to my S, I'd have R, R prime, R double prime. And so on and so forth.
Why, go back to the board to the QS wave, why is that not a QR wave? Because it's negatively deflecting and then it goes up so that.
There is no positive deflection above the baseline.
Okay,
So the deflections are always in relation to the baseline.
okay.
So this never had a deflection that went above the baseline, so therefore it never had a positive deflection in it.
Okay.
Yeah, that's a great question. Everything is always in relation to the baseline, which means you have to find the baseline first. You have to know where the baseline is to know if something is positively deflected from the baseline or negatively deflected from the baseline.
Didn't you say before that the deflection, either positive or negative, depends on how the cameras are oriented?
Absolutely. How the signal is in relation to where the cameras are oriented.
Okay, so if that was oriented opposite as it should be, wouldn't that just be an R wave?
Yeah, that's exactly right. So if I had this on my EKG, what do I have? I have an R wave. That's right.
So can you look at, so if you're looking at reciprocal changes and you have you're seeing a QS wave, that exact same rhythm on the opposite side will be just an R wave.
I would expect it to just be an R wave. That's
Okay.
correct.
And then the negative deflections between R and R prime, there's no designation for those.
It depends. It depends.
If it goes below the baseline?
No. This is where we get a little bit shaky on EKG. We have to make a determination that we get through just experience of looking at them, and you'll look at lots of them. But this is likely not an S wave. This is just the finishing of this R wave, and then this R wave comes in after. But it is possible that we have a wave that is this, where this is an R, this is an S, and this is, I'm sorry, an R prime over here. And when we discuss this as being an S wave, depends on a whole lot of factors. It depends on what's causing this second R wave and the timing of it, and what we are expecting this to have done. So if this is pathological in some fashion. But the question that we have to ask ourselves is, if this was not there, would we have resulted in that? But we didn't get that because an R wave came in on top of that S wave. And that's some question that has to come based on what we see clinically with the patient and some experience of looking at some EKGs on whether or not we have an S wave there or not. I will also tell you that you might see this. Right? And this is an S wave.
Is that R prime?
This is an R prime wave. That's correct.
Do you call
That is
it,
definitely an R.
do you call it an R prime S wave or
Yes.
just R S?
So we still call this the QRS complex, but we would write it as an R prime S wave.
Okay, so
And that
you
way,
would say
anybody who
that.
reads it would know exactly what we saw. But when we talk about it, we still talk, hey, that QRS complex has an R prime.
I can't quite see from here. Are you putting R1 or are you putting R?
R with an apostrophe after it for
Oh,
prime.
okay.
Is that better for a moment?
No, I can't see
Fantastic.
that part.
Perfect.
Optimus.
Good. Okay. Are we good on that? Okay. So nomenclature.
What does that word mean?
Nomenclature means how we are writing things down, how we are referring to them when we want to write and make people understand what we saw. Big waves in proportion to both that wave and in proportion to everything else we're seeing in the patient. So there is a little bit of subjectivity to this, I understand. But when we see a big wave, we use a capital letter. And when we see a small wave, we use a lowercase letter. So when I'm writing this one right here, proportionally, I have a tiny R wave, a big R wave, and a big S wave. So I would write little r, big R prime, big S wave. This is capital Q, capital S. This right here would be a little q, big R, big S. This right here would be a little r, big S, okay, when we write it.
What defines tall or small, like certain?
Excellent
millimeters?
question. I don't have an answer for you.
Oh.
It's somewhat subjective, and it is in relation to, it's in a comparison within that person's own set of QRS complexes that we see throughout all of the leads we're looking at.
So kind of eyeballing it?
We do, to a certain degree. That's correct. Okay, and so our QRS complex is right there. Yay. Yay for the QRS complex. You can see all kinds of different possibilities that are there. Right? It can come in many, many different shapes, many, many different ways.
Well, I don't know if you would, like, what physiologically happens to two R and R and R? Huh?
How many ventricles do you have?
So there's, well then you said you go prime, R prime, and then R prime two, you go like double
Yes,
prime.
so
and
if you end up with several pacemakers that are all working at once, you might have several different portions of the heart, of the ventricles that are now firing independently on each other. And remember that this is an electrical activity. This is an electrical activity that we hope is translating to a muscular activity, but it doesn't have to. Those are two different things. We have electrical activity happening, and we have blood pumping. Ideally, the electrical activity is forcing the muscle to do the pumping. But if the electrical activity gets disrupted, it might not cause the pumping that we're looking for.
So then what you're saying is when we see two R waves, the ventricles are constricting at the same time.
Well, there might be some overlap of when they're contracting at the same time, but there is a delay of some sort that is causing one to contract at a slightly different time than normal.
So could that be when it comes down and it breaks into the two bundle branches, they're not traveling at the same speed and won't compress over the
Yes.
other?
Like, for example, if one of those bundle branches is blocked,
Oh my
and
gosh.
one side is going normally, and the other side is taking longer because it has to go through the gap junctions instead of the Purkinje system, as an example.
I might be completely off, but the side, the left to right bundle branch block is correlates to where the small, the smaller R would be, like the one far left would be a left bundle branch block.
No, you can't make that correlation. Whether or not it's left or right depends on other factors that are coming into play. So whether or not this is the left and this is the right, or this is the right and this is the left, completely depends on which one's blocked and where the camera actually is.